abstract representation of the world. So objects is one of them, but it's not the only one. Like, how do we build or learn models of the world that allow us to not just predict but also reason? Like, we can simulate a lot of stuff in our heads. We seem to have a configurable model of the world that allows us to kind of apprehend any new situation we face, and that will probably go through something like causal inference that Leon is fond of, and self-supervised learning of some sort, and dealing with uncertainty, as I mentioned in my talk. But really, that's the big mystery. So there's a theoretical question related to this, which is there was an argument that I believed for a very long time on my own, and then discovered that Vapnik had kind of the same argument, which is that you should never try to solve a problem that's more complicated than the one that you're facing. And so if you're facing a classification problem, you should learn the classification problem directly and not try to learn a generative model of your data before you learn the classification problem. I think this argument is wrong. I completely changed my mind about this about 15 years ago. And the 15 years before that, I had endless discussions with Jeff Hinton because he was trying to convince me of this, and I wouldn't hear it. And so that's kind of prompted me to, basically observing how fast humans and animals learn, I think prompted me to say we have to have some sort of efficient way of learning representations in a task-independent way that doesn't put us in jeopardy and that exploits all the information that is kind of flowing through our senses. And we need machines to be able to do this as well, because we're not going to be able to learn all the tasks that we need machines to do in the world by training them in supervised or reinforcement learning mode. They'll need to learn how the world works, in this kind of a more generic fashion. So that's, maybe there is some theoretical questions behind this, which is, is there an intrinsic advantage in learning the structure of the data in a task-independent way before you learn a task, right? And it's not clear to me that there is a good sort of theoretical framework for explaining this of the type that we have in sort of classical learning theory. Okay, that's one thing. And then the other questions I think that are related to what people have talked about in the last couple of days is I still struggle with sort of having a good intuition for what the landscape of objective functions look like in high dimension. I mean, we all struggle with this, but it's very odd. But there is this idea somehow that there is only one minimum, essentially, or only one that's useful. That high local minima are either in very small number, and therefore we have a very low probability of getting trapped into them, or they just don't exist because in 10 million dimension or 100 million dimension, it's very hard to build a box. You need many walls, and the type of parameterization we use in neural nets basically make it somewhat difficult to build a local minimum. So maybe that's an explanation. I think there's been a lot of work on trying to understand the landscape, and I don't think we've got to the point where we're done with it. I think we understand more and more, but not everything. Then there is the mystery of, which was the topic of a lot of talks this afternoon. Why is it that widely overparameterized neural nets generalize? Okay, and we've known this experimentally for over 30 years, but it's still somewhat of a mystery. Is it the case that SGD actually helps? Is it the case that this story about flat minima versus narrow and deep ones, and you prefer the flat ones? There's a lot of evidence for this, but is it really true? And this sort of kind of double dip type, the peak at that we heard from Misha Belkin and others. It's something also that experimentally has been known for a very long time. There's actually a few papers from the early 90s at NIPS on this kind of stuff. This was when people were studying teacher network and student network, right? So you have a teacher network that you use to generate data to train a student network. And if the student network is smaller than the teacher network, it's easy to train. It gives you crappy performance, but it's easy to train. If it's much bigger than the teacher network, it's also easy to train and it works well. If it's exactly the right size, then you basically can't train it to match the teacher network, and you have this sort of phase transition in between, which corresponds to the peak that Misha was talking about. So, those are sort of puzzling theoretical questions for me. Have to do with non-optimization, or we need a new name for this. Huh?
Training. I call it training.
Yeah, training, but that's a little too generic. And generalization.
Yeah, so in general, I think this has actually been a really fantastic workshop, and I've learned a ton of interesting things. I mean, for me, the single thing that stands out most is Misha Belkin's talk. I just think that was sort of so fantastic, and maybe I've been living under a rock for the last year, but I hadn't seen a coherent presentation of double descent. And I think for a long time there was sort of a feeling among deep learning practitioners that there was just this huge disconnect between learning theory and what people were seeing when they were training these huge neural nets and just continuing to train them. And even when you'd sort of gone past the sane point of training in terms of your training set error being virtually zero. And I think it's just fantastic that we're now starting to have somewhat more understanding of what might be going on there. In terms of what I'd like to see more of, this is a bit dangerous since Jan's sitting right on my left. Jan's talk was also really interesting, but then once it got into the energy-based learning, I'm not sure if what I need is more theory or an algorithm or just to go and read some papers. But I thought it was really interesting, but at the end of the talk I had no idea how I could take energy-based learning and actually use it to solve doing self-supervised learning of a video. So there's something that I'm missing, or that the field's still missing.
Yes. So I could somehow divide the talks in two categories. First category is, why is it that neural networks generalize so well and so efficiently? The second category is, there is a serious problem. They're not generalizing well enough by any measure. And I'm more interested by the second category. Why don't they generalize well enough, and what can we do to make them work better? It's like that probably because I've been so used to seeing neural nets working efficiently for a couple of decades that I don't pay attention anymore. But in fact, I was completely wrong, because what I've seen in recent work is that when people in theory start looking at the empirical fact and see how the empirical facts are different from the existing models, they invent new ones, and they do very interesting things. Like, for instance, all the recent results of the over-parameterized or interpolating regime, both in terms of speed of convergence and in terms of generalization, are very interesting. And they might actually help the other problem, which is to make them work better. Oh, okay. So should I repeat everything? So there is this aspect that we understand a lot more things, and that's very interesting. Actually, it's going faster than I expected. Now, the second part, which is neural networks are not working nearly well enough to be up to the hype, I think it's a serious concern. And it's a problem of a different nature because we're missing the essential statements about what you're supposed to do. When I say why deep learning generalizes so well, I'm speaking of normal generalization in distribution. When I'm speaking why they're not nearly good enough, now we're speaking of art of distributions, about transfer, about what's happening when people are exposed to situations that are maybe related to things they've seen before, but clearly not the core of the distribution that they've seen before. And this challenges a lot of the statistical grounds of machine learning, and I think it's going to be very interesting, and I'm looking forward to see how all of you are going to find a way to navigate the bushes.
Okay. I agree with many of the things you said, especially with what Leon said. So instead of repeating exactly what he said, I want to highlight, you said what was interesting, I want to highlight two papers, both of them were actually discussed here today, that I found very interesting in the past few months. One is a paper, is a work by Zico Coulter and you'll have to help me. I know you're here. Vaishnav. Okay. That asks the basic question of we've been trying to explain things with tools of uniform convergence, and I don't completely agree that's the only tool, but I think that's a paper that proposes a very nice formalization of the question of is this tool, can this tool at least at all work, rather than just trying various things and seeing does any one of these particular approaches using uniform convergence work, and also provide specific examples in which they show that no use of uniform convergence would work. The other paper is by Alan Zhu and Lee. We also heard it, I guess it wasn't presented here, but we heard it discussed, I think, in one of the talks. There's been many results in positive results about things that can be learned using neural nets in the past few years, coming from a theory community, saying if we have a problem of this form, then we can train a neural net and it'll also generalize. All of these results were actually of learning very easy things, in particular things you could also easily learn with linear models, with kernels. And so even though they do say, we have all these complicated models and say you have just a problem that's linearly separable, and look, we train this super complicated model and can learn a linear separator. Okay, that's a non-trivial mathematical statement, but it's very disappointing if that's the only thing we can say about kernels. And this is the first result that provides some type of positive result that goes beyond what we can already know to do with kernels. And in terms of, so this leads me also to the question of where I would like to see more work. So first of all, I completely agree with Lone, but again, I'm not going to repeat it about wanting to explain what we know so we can go further. But one particular question is really, do neural networks actually go beyond kernels? So this is something that I think the jury is still out on. I know that some people here have definite opinions on that, but there are other people, there are other people that I respect very well doing empirical work that actually feel that no, that actually if you just design the right kernel, then anything that Jan can do with a super fancy network, then just if we use the right kernel, we could also do it with a kernel. And also from a theoretical perspective, it's been extremely difficult to actually demonstrate something that we can do with a neural net that we can provably not do with a kernel. And this is very disappointing in some sense, because neural nets in some sense are much more powerful. Definitely if we could actually didn't have optimization, we could solve the optimization problem, we could just do ERM on a neural network, then we know we can go way, way beyond kernels. And the question of if we actually train a neural net with gradient descent or with any type of local search, can we go beyond kernels or not, is I think a very interesting theoretical question, or also a real question. I think it's not completely clear to me which way this goes.
I have my own. So let's start with the raves. It's pretty incredible in that I was talking to Sanjeev, like 4 years ago, it seemed like it would be impossible to get any handle on deep learning. It just seemed like a gigantic mess, these huge networks. And now it seems like we have some near to honest explanations in this asymptotic regime that really do seem to match practice. So I think this is pretty unbelievable. The NTK stuff, Misha's work, and it seems plausible that we're going to push this and really start pinning down when these regimes kick in. So in terms of new directions, let's see, I'll push back on Jan a little. So I definitely think that RL and interactive learning are actually important, because we do need agents to interact with the world. The distributions change all the time because we do have impact on the world. I'm also pretty sympathetic to wanting simple procedures and direct procedures to solve these problems. But the conclusion I'm partly reaching is maybe an agreement with Jan that we do actually, to solve the interactive learning problem, even directly, there's good reason to believe we need to start incorporating dynamics information and interactively learning models of the world, even for solving this pure RL problem.
So I'd like to express a disagreement here.
Hold it closer.
I'd like to express a disagreement about the NTK thing. First of all, the NTK thing is very interesting because it gives at least a proof of existence that in a large enough deep learning, you can find a solution, provided you in a certain regime. But there is another paper. There is the Shiza paper is very interesting. The Shiza paper essentially had two parts. The part number one says this regime can be recreated in plenty of nonlinear systems by properly scaling the inputs. And the second part is a bunch of empirical results showing that, when I'm in this regime, I underperform in terms of test error compared to other regimes. And so I asked Francis Bach, who is one of the authors. And so I cannot speak for him, but this is what I understood from what he told me. So he told me, I would love deep learning to be the same as a kernel, but I know it's not true. Overwhelming empirical evidence is not true. So there is something else to be found there, and that one's going to find someday.
Yeah. So again, I'm going to completely agree with Leon. In particular, let me refine what I said before in reference to the NTK. If we want to understand how neural nets are more powerful than kernels, or ask if they're more powerful than kernels, understand where, then the NTK is definitely completely the wrong place to look, because all it says is, well, that's just a kernel. So.
There's one way in which I agree with you, which is that if you find the right kernel, you can do whatever you want, right?
No, that's not true.
Well, it is.
They're learning problems. No, they're learning problems that you cannot solve with any kernel.
Well, of course, but then you would not be able to solve them with neural nets either.
No,
right?
no, that's if you could actually solve the ARM problem for neural nets, then there are problems even for two-layer neural nets. Then you could solve learning problems that you cannot solve, you provably cannot solve using any kernel. So this. Well, if you have something to learn, then it has to be family. I mean, if you're...
It might mean under limited resource in terms of training examples.
No,
right?
oh, well, of course. I mean, you want to learn with limited training examples, with finite training examples.
If you have infinite training examples, which is not completely unrealistic these days.
I don't completely agree. I mean, even when you say infinite training examples, you have tons of infinite examples. Tons is still not infinite. Like, because, I mean, the amount, I mean, this is... Like, I want to talk about polynomial versus exponential. I don't know how you want to turn scaling, but I don't think that thinking about infinite data is useful here.
I think it's a misunderstanding. Jan meant a kernel expansion can pretty much approximate any function we want.
Yeah, but okay,
but you don't even need to have the right kernel.
Right, any kernel. Right.
Any universal kernel is going to do that.
Right.
And your point is that if you have data that's limited, as is not exponential in quantity, then that might not be true anymore. And there is a valid theoretical question is to find the limit exactly, but that's another story.
By the way, people from the audience who have questions, you can start lining up. Should I ask another question from Twitter, or is the discussion still going? Let's see. Well, one question is from Venkat Ramaswamy. To what extent do you think the theory of deep learning, he puts the in quotes, will inform the question of how the brain works? Anyone wants to take that?
Okay, well, there's a point I made a few months ago in this very room, responding to, within a workshop that Sanjeev organized about the epistemology of deep learning. And the point I was making is that people, like if you look at the history of technology, there's a lot of artifacts that people have invented way before they were understood theoretically, and then the theory came later. A good example is the steam engine. So the steam engine was invented about 100 years before the thermodynamics was basically put together. It's the same with the telescope and a lot of phenomena. Certainly, radio communication was invented way before information theory. So very often the theory is developed to explain or figure out the limits of a particular artifact. And I think the interesting thing about deep learning and the fact that it has some commonality with human and animal learning is that perhaps it will drive people to come up with some theoretical framework that explains intelligence and learning independently of what the underlying substrate is. So I'm sort of after the equivalent of, aerodynamics explains how birds and airplanes fly. both of them, even though the details are very different in the implementation. So perhaps there will be sort of the equivalent for intelligence that explains both how machines can learn and become intelligent as well as humans and animals. But I don't know what that is. Ultimately, I think it will help, because what's missing in neuroscience today is some sort of general understanding of the functioning of the brain at the systems level. Like, every single learning algorithm that we come up with minimizes an objective function somehow, maybe badly. And we don't know if the brain minimizes any kind of objective function. If it does, we don't know how it estimates the gradient. It probably does estimate the gradient. It would be crazy not to. It would be horribly inefficient not to. But we don't know how. And we certainly don't know what the underlying paradigm is. So I think theory will help understand how the brain works, yes.
So I think you can give a sharp answer.
You really need to get closer.
So I can give a sharp answer. The question is, does the theory of deep learning inform us about how the brain works? And fact number one, deep learning is nowhere good enough as a model of how the brain works. The brain works much better. Fact number two.
The question was something. Does it say something? Maybe, yeah.
Yeah, the number two is that the theory of deep learning has made huge progress, but there is still a lot of unknown things. So the answer is no twice, I think.
Not yet.
Maybe later, but.
Come on, guys. No, nobody wants to ask a question? Anybody? Oh, please.
Thank you all. Okay, thank you all. My question is about, my name is Amin, I'm from University of Georgia. My concern is more from a conceptual / philosophical point of view, and it has to do with question and answering in NLP. I'm kind of pointing to you two. So the worry is that on the one hand, I think I take language to be a communal phenomena, and I take the clues from Wittgenstein, which is arguably, argues for language to be a rule-following behavior in a community. So if you take that seriously, it means that we need to, if you want to develop a question and answering system, and which is based on some form of inference, we need to pay attention to communal rules in determining the content and also determining the rules of inference in certain language game. But that goes against, I think, the current project of question and answering, which I think is trying to come up with a kind of omniscient agent who can answer whatever question is being asked, and it's not parochial enough or it's not communal enough to be specific about questions that a single user might have. So I think the parochial and communal aspect of language is being ignored in the current question answering algorithm that I've seen. Thank you.
I would like to see systems which aren't trying to come up with some omnipotent answer to a question, but would rather read everything that everybody's said on the web that is relevant to answering that question and somehow synthesize and summarize and put together those things. So I think it's very much making sense of other people's opinions and what has been said. There are very cut and dry questions, like, what is the birth date of Barack Obama or something, which have a very clear answer. But the really interesting questions are the kind of questions that historians or social scientists, economists study and write essays about and write books about. And those are the kind of questions that I'd like to see a QA system really answering. I think we're a ways off that. But that would require reading everything and synthesizing everything, I think.
I think the answer I'd give is, partly you are right. So in language, there is very small community parochial effects and usages of words and ways of speaking which will be largely opaque to people outside those communities. And so to the extent that being able to answer a question depends on having an understanding of this very parochial language use, then trying to build universal, or at least universal for one language, question answering system would be a complete failure. But on the other hand, language is also a communication system that is used on a very large scale. And normally there becomes some more conventionalized form of language that is broadly shared. So to a first approximation, all English speakers can understand what each other writes, and all Chinese speakers can, or various Chinese language speakers can understand what gets written in Chinese. So that there then become these sort of broadly shared communication mechanisms. And I think really what we're saying is that the kind of question answering systems that we're building are meant to work with the standardized written languages for broad communication, which is what you find on your web pages or Wikipedia that you're answering questions from. And yeah, maybe these would go badly wrong if I went off and collected some data from inner city Chicago and said, answer your questions on those.
Question for the NLP related to this. So, there is this current deep learning paradigm. We're just going to build a big language model and predict a few missing words. And it does seem like there's this direction. We're just going to start linking this up to databases. And the more and more we do this, it seems we're just getting more and more impressive results at things that what I would think are going toward genuinely hard long-term dependencies and understanding. But in the back of my mind, I feel like it can't go the distance, but I feel like I'm not going to bet against this approach for any time soon. And that's what, and I would not be surprised if things that I thought were very hard to do, that somehow required real understanding, are just going to be solved by taking some big database, and cobbling together some stuff with missing words. And I'm wondering what the NLP folks think about, this current approach.
Basically, I agree with everything that you said. On the one hand, there just seems to be a ton missing. On the other hand, it seems like you just can't bet against it at the moment, and the speed at which things are getting better is fantastic. But I think the kind of picture you get, for the question answering systems that both Mike and I talked about some, that if on the one hand, the progress that there's been made in doing this question answering from text is just amazing. And so you can start to see that sort of now being deployed in places like Google, where there's now just sort of good question answering compared to the old level of, okay, I'm going to return a web page to you. It's totally amazing. But, the extent to which these systems can get questions right on data sets like Squad, it sort of blows my mind how good they are. But on the other hand, if you look at what they're doing, approximately what they're doing seems to be that they can look at the words in the question and say, okay, the semantic type of the answer here is a temperature, a person's name, a year. It then does just kind of a general semantic match. Where in the text are their words most similar to the words in the question? Okay, then let me look for an entity of the right type near to those words, and I'll find the nearest one, or I'll guess one of the close ones. It's really no more intelligent than that. It doesn't seem to actually be understanding human language at all. So there is just despite the high performance numbers, there's just a huge amount of understanding that's still being missed out on.
Yeah, I agree with all of that, and I'll just add one thing, which is we have gone really long way on sort of one-shot question answering, where you take a question and you answer it, or for that matter, machine translation. The results there are pretty remarkable, although they're still flawed. But have you ever had a conversation with an end-to-end learned system? Or anything close to a conversation? That's what language, at the end of the day, a large part of it is about conversational interactions, where a machine would have to track what is being spoke about in the discourse and make inferences and make responses and so on. And I think seeing how we would make progress on that problem using deep learning is extremely intimidating. Because I don't even know how to collect data in that domain. I really don't how to make a start on that domain.
I have a question about that. So, given that Alexa and company are in every home, and now we have billions of sentences of communication, Is that helping that effort? No?
Jan's got an answer.
I guess you're not allowed to say it on
No,
the
it's
record.
it's not helping particularly. It's not helping. No, I mean, you know, the big machine learning stuff in Alexa is to basically classify, you know, from the utterance, which one of the 80 things that it can do, it needs to do, right? Is it, you know, giving traffic or weather or playing a piece of music or whatever? So there is some sort of end-to-end trained system for that, but you know, other than that, it's a lot of basically handcrafted heuristics. No, I mean, there's a lot of work at Facebook, you know, by Jason Weston among others on end-to-end learning of dialogue systems. It's making progress. There's even some sort of chatbot you can play with on Facebook Messenger that they put out. As long as the dialogue is meant to be entertaining, it's fine. As soon as it needs to be useful, it becomes a lot harder. Yeah.
We should take a question. So this is not on. There's one button at the bottom. See if you can turn it. It's slides, yeah. Very small button. Well, you can also come here. Try to check that.
Hello, so I'm Da Liang from Harvard. I'm a physicist, so I'm pretty new to this field. So one thing I'm really wondering about NLP is that, like you said, there's this huge gap between what the machine can do and what the real understanding of language is. So do you think there is a practical way to address that, in particular natural language grounding? And what are some of the ways that you can make progress in this direction? In particular, is there a way to combine NLP with computer vision to really produce like grounded languages based on visual features?
There's quite a bit of work on this, actually, particularly at Facebook. There's a project called Habitat, which is basically a virtual environment for a robot, and you can have sort of dialogue interactions with that robot. You know, one of the main things there is that you need to create those virtual environments where you can have interactions and you can test, you know, new algorithms. But then there is the big conceptual question of, you know, do we need grounding to reach human level AI or something like that, right? And it's kind of surprising that you can get, you know, 90% correct on Winograd schemas with transformers, you know, pre-trained, you know, BERT-like. Even though the entire AI community was heralding the Winograd schemas as an example of things for which you would need common sense to be able to solve them. And so the performance went, I mean, the best systems went from 60% correct to 90% correct because of BERT-like pre-training, basically. So it's not yet to the human level, which is 95%, which probably requires a bit more kind of knowledge of how the world works behind the scenes. But it's surprising how far you can go without any grounding. Ultimately, I think we need grounding, though.
Yeah. I think the question of grounding gets more complex the more you look at it. Because, I mean, it seems very simple at first. You've got some words and you've got your image or video and you're sort of grounding between one and the other. But, you know, you can also just ground from one piece of language to another piece of language. And you can ground from, you know, one human language to a different human language, right? There are lots of ways in which you can put alignments between things, and it's very unclear, you know, which ones you should privilege how. You know, that being said, I do believe strongly that, you know, little humans benefit greatly from being in a physical world and getting input from that world as well as input from language. So, you know, if you're a grad student now and you're very ambitious and you either want to succeed big or fail big, I think doing grounded language learning would be a really exciting area to get into. But it's still an extremely challenging area to make progress compared to, you know, just just doing what Bert's doing and training from a few billion words of text. So you've got to realize that I think there's still, for at least the next 5 years, probably a larger chance that you'll fail big rather than succeed big.
Yeah, I mean, one point I forgot to make is that, I like orangutans, right? I showed an orangutan in my talk. Orangutans are almost as smart as we are. We think we're much smarter than them, but we're not considerably smarter than them. They don't have language. They have very little interaction with each other. The only interaction is between mother and child. All of their knowledge basically is physical and perceptual. It's very little. There is communication, of course, but very little language of the type of bandwidth that we have as humans. And then you go to, I don't know, octopus. They never actually meet their parents. The mother dies as soon as the eggs hatch, and they're incredibly smart. They have problem-solving capabilities and all kinds of stuff that are pretty amazing. They only live 2 years. It's just incredible, right? So how do they do that? And it's all, there's no language. I mean, they have some funny language, but by changing their color and stuff.
So just quick interjection. Discussing future of AI is a sort of much bigger question. So, but please continue. Yeah, and we can then take more questions.
I'll just disagree with Jan on that one. I think Jan really, really underappreciates the importance of communication, right? And so, I've heard Jan say several times that, orangutans are about as intelligent as human beings. And, well, I think that's sort of true at the level if you sort of had one human being by themselves, right? And that's where, not that many thousand years ago, there were sort of individual hominids living in caves, and they weren't that more intelligent than orangutan. But, the huge difference is that humans developed communication mechanisms and, first spoken and be able to communicate with each other. They could share knowledge and wisdom, and so the society became much more intelligent and people worked out technologies and ways to do things. And then we developed writing so we could transfer knowledge across time and space. And, that's been so amazing, right? That's in about 5,000 years taken us from, chipping away a few stone axes till we now have our sort of mobile phones and other fantastic accomplishments. And that's because we developed societal intelligence. So I'd like to say that, humans, where you have a society, are clearly just orders of magnitude more intelligent than orangutans are.
I kind of agree with that as the other language person in the room, but I'll hand up to you.
Okay, 3 words. Our brain is only twice as big as theirs.
So this is partly a follow-up and a question for Jan and Sanjeev on this. So Chris's point just about these kind of semantic relationships that we get with BERT and things like that, we haven't even begun incorporating realistically information from databases in our progress. So I feel like when we start doing that, I think it'll make it these questions even more pressing. But I guess the question to rephrase Sanjeev, forget about Alexa per se. You were talking about interaction a lot, Jan, but in your talk, you're like, just learn dynamics. But I think the question in my mind, there's one model of approach, just get lots of databases, get lots of language, try to cobble this all together with tricks. And there certainly seems like we're going to go pretty far, but fundamentally, what is the role of interaction in learning language, and where will we need that? And so partly theoretically, do we have any reason to believe what's the role of communication and learning? So maybe Sanjeev for that, and how we think about that, and even just intuition for empirically, because the current push is going to be impressive, but you've said interaction many times. So at which point do we actually need to do any type of interaction to effectively improve things?
I guess people have been trying to develop a theory of interactive learning, and I think where it's not gone so far is that it has to involve some notion of representation. There's some hierarchy of concepts and things like that, and so that's where the teacher can help, and that's why we go from kindergarten to PhD, and so this hierarchical nature of knowledge must be somehow capturable by theory, it feels, and it's a nice project.
curious to hear the question from the gentleman here.
Okay. Hi, I'm Clayton. I'm a new grad student at Columbia. I was interested, based on the talks earlier, we've talked a bit about how we're moving into this, or how a lot of neural nets fall into this interpolation regime, where we are interpolating the data and vastly over parameterizing and it's working well, and that a lot of classical analysis doesn't apply so much. And I'd like to ask whether, to what extent the panelists think that the classical capacity-based analysis, Rademacher VC type things, are still going to be relevant moving forward for neural nets.
So I think that we have to separate between two things here. One is highly over-parameterized models, and that's something that we actually can handle very well. I mean, I say we, it's before I existed, right? I mean, the community has had tools for handling infinite dimensional models for a long time, and that we can handle. The interpolation learning is a challenge that, if you're looking back, existed, always existed. I mean, Jan mentioned some results from the early 90s. If you look back at papers I looked at papers at least from the late 90s, and you can see those plots that hit zero training error, and we're getting good results. I'm referring, for example, to some of the experiments people did with boosting, trying to understand boosting, and people focused on this issue of where is the regularization coming from. They realized that, and that was addressed, but completely missed the fact in retrospect that it's interpolation learning in a noisy regime that the theory developed didn't actually explain. And you see that in many cases. And I don't think that means we should abandon all the tools we have. It means that we need to refine them, which we are doing. We heard some talks about it today. And so I do think that definitely the tools we had the tools we have, including tools from uniform convergence or some notions of local uniform convergence or uniform convergence combined with other things, we know how to refine we do know how to get generalization guarantees, even if we don't have any kind of uniform convergence, even any kind of local uniform convergence or algorithmic dependent uniform convergence. We do need to keep refining these techniques, but we shouldn't throw them away. So in particular, one thing I just want to emphasize is that it's important to also learn and understand all these things. The theory we've been developing for the past 30, 40 years is still, I think, a very useful basis.
In high-dimensional spaces, for any practical number of samples, there is no such thing as interpolation. Everything is extrapolation.
Hello, so this is Peng Chuan from Microsoft Research. So I'm mainly working on developing optimization algorithms for deep learning and also train large models for kind of practical use. So my question is about the training of deep models. So on the high level, I want to know from your perspective, how close we can bring the training of deep neural networks to the training of convex models. You can see that for convex optimization, so it's very easy to reproduce. So you can even think that the training process is just, you do not need to understand it. You specify the loss function, and then you can trust any optimizer so that it will give you a result and you can reproduce it. But deep learning is not like this. For example, for BERT, I think after Google produced the result, and it needed, I think, more than 1 month for the second company, the Hugging Face, to reproduce their result. There's a lot of magics or black magic in the deep learning models, not only in the model design, but also in the optimization to reproduce this result. It's very brittle. So I want to know that on what level you are happy with the training of deep neural networks. What kind of magic can be removed and what kind of magic must be there?
Well, this is also a question that we discussed during the workshop that Sanjeev organized a few months ago. Whether deep learning is engineering science or alchemy. But so, I mean, there is a lot of black art in making neural nets work. A lot of it is built into the software that PyTorch or TensorFlow or whatever that you download. A lot of it is just personal experience, and it used to be. It's probably the case that part of the reason why people abandoned neural nets in the mid-90s was that there was no good way of distributing those techniques. Nobody was interested in reading about them in a paper, and very few groups were able to distribute their code in open source because it wasn't standardized as it is today. And so basically it died because a lot of people would implement backprop and there was some bug in it, or they did something wrong and it didn't work, and they just assumed neural nets didn't work. So there was this reputation that only a few people in the world could make neural nets work, right? Which obviously is not the case because a lot of people now train neural nets. So yeah, there is a bit of that, but that's just called engineering. That's what engineering is all about. It's the expertise to actually build something and making it work. That's all of engineering is all about that. So now the question is there some recipe that you can apply supported by theory that will make neural net training reliable, so it's just turnkey, just turn the crank. And it's coming pretty close to this in many cases. It's nothing that's completely provable, but it's pretty reliable. When you train a ResNet on some image data set, it's pretty repeatable. You don't get exactly the same error rate every time, but it's pretty close, right, every time. So, non-convexity is not the issue there, right? I mean, you can insist that the model you train are convex, but then you're throwing the baby with the bathwater.
I think for image nets, it's reproducible, but for more bigger or new models, spurts or this kind of thing, it's still very difficult to.
I have an example. Yeah. Suppose you're a mechanical engineer, you're making petrol engines. These things, petrol engines, these things that you have in automobiles that make them go forward. There's a lot of black art there. Now, your competitor comes with a new one that's a little bit more efficient. How long does it take you to reproduce this? Oh, it's not 1 month. It can be 1 year, 2 years. So I think we've been spoiled by the fact that computer science is typically easier to replicate something because the recipe is very strict. But when the fact that there is a lot of black art in machine learning or in deep learning is no different than the lot of black art that you have in a lot of let's say, engineering disciplines, like making petrol engines, or making weather models, or making a lot of things. Even a simple radiator that the kind you have in your home is full of black art. And so we know how to do with these things.
So I don't agree here with Jan and Leon. So, I mean, the reason that it's going to take you a long time to catch up with the competitor is the competitor is not going to tell you what they did. And the problem is that this is not exactly the same as researchers actually telling you what they did, and you still have a long time catching up with them. I think those are two very, very different things. And I don't accept the fact that engineering is just going around, trying this and following some recipe. I think this is exactly, maybe if you mention alchemy, this is maybe exactly the difference in alchemy in engineering. Alchemy is following a recipe. You have a recipe, and and as I think Ali pointed out, these recipes, many of them work. You have a recipe and you're just following the recipe, but it's not based on any foundational principles. I mean, maybe you have some feeling of what's going on, and to me, this is maybe the main difference in that and engineering. Whereas engineering, it's true that engineering does involve a lot of exploration, and you don't always have. It's not that, in almost any real engineering, you don't have, it's not that things behave exactly, you can, without doing any experiment, just write the formulas and know what's going to happen. But you have fundamental principles, foundational principles that you use them and you understand them, and you understand at least the space you're exploring. And this is not the case right now for machine learning. And so I still think that there's a lot of catching up to do in order to say that what we're doing is engineering. And going back to the original question, yes, I think there's a very big difference in terms of the role of optimization between convex models and convex learning, or most of convex learning, and deep learning. And I think maybe touch on that a bit tomorrow. But much of convex learning can be phrased in terms of an argument. And the optimization problem there is just, it's besides the point. I mean, it's just a way of solving the argument, as you pointed out. So I don't need to worry about that. Both I don't need to worry about for two reasons. One is because I know how to solve argument problems for convex optimization. So I don't have to worry about too much about, oh, can I solve the argument? And the second is it doesn't matter how I solve the argument, I'm going to get to a solution. And I would argue that deep learning is not an argument. It's not even a situation where it's an argument and it's just, oh, maybe hard to solve that argument. The entire inductive bias, the entire description of how what the learning is, the way that's actually the learning is happening, is through the way you do this local search. Because the argument is trivial. You can get zero error, and it's very easy to get zero error. And the question is, which zero-S solution are you gonna find? And so it's the whole. Everything is inside that optimization algorithm. This is a very big difference from what we've been, the way we've been thinking of learning in the previous decade.
Do you have a comeback, or should we go to the next question? Okay. Metra, you've been waiting.
Yeah, so this question is pretty broad, but I'm still very curious to get your thoughts. Is there a particular idea, or not paper, but just sort of general idea in our field, in maybe the recent pulse, like maybe the past year or so, that's really got you excited?
Our field.
Yeah, so deep learning theory, but I think also deep learning more broadly. Is there some idea there that's that kind of really stuck with you and got you excited?
I think, well, we're seeing a lot of advances, but what's exciting to me, it seems like density estimation-based models are, the Gans things were impressive, but we're seeing like multiple ways to actually do density estimation that seems to be working far, far better than before. And for me, this has been impressive, like language generation, the image generation with genuine density estimation models and not Gans. Like, I've been pretty excited about that. I think that was super cool. Models are starting to work.
Yeah, I would say, Gans. I mean, I'm on record saying Gans is the best idea in the last 10 years in machine learning. I still think, Gans are really great. They're a complete pain in the ass, pardon my French. And they have fundamental problems in their formulation, which, Leon partially fixed with the Wasserstein Gans, but it's related to the point I was making this morning, that if you insist that Gans learns some sort of distribution, you end up with a discriminator that needs to have infinite weights and produces a golf course type surface, which is not useful for anything. But so I don't think they are formulated properly. But the general idea of training a neural net to produce contrastive samples to train an energy model, I think is very good. So I think there's a lot of effort in those generative models of various kinds, latent variable models, VAE, VQVAE, the sparse models I talked about, various ways of regularizing the latent variables that I talked about. So I think there is, I still think we don't have the recipe. I don't think Gans is the ultimate recipe. The problem with Gans is that training, you have to train the objective function, because by sampling the latent variable, there's no way that the stuff you're going to reconstruct is going to be the stuff that you're observing. So now your objective function has to be, your cost function that you plug on top of it, the discriminator, has to be really complicated. So there's a lot of hope that somehow we'll find a good way of basically doing prediction or reconstruction with uncertainty. That's what I'm completely focused on. So that's what I think is the most exciting thing. Yeah.
So just a quick clarification. So the specific thing I was excited about in this space is that likelihood-based models we're seeing good results for.
Right. And what I'm excited about is non-likelihood-based models.
Well, I'm mostly excited that with all the excitement about what's happening now, and we have the freedom to actually look further. Like, for instance, we had the talk of Sanjeev saying this is not optimization. But if you think about it, the criteria we optimize, between quotes, or the criteria we use as a benchmark are hopelessly inadequate. I'll take an example in, let's say, language models. Typically, we evaluate them by a kind of likelihood, or basically by the number of bits they encode, not by perplexity. And Shannon, a while ago, tried to estimate the number of bits per letter in English. And this letter has been refined by people in Brown later on, I believe. I think you know that better than me. And I don't remember exactly the number, but I remember that the difference between this and the best n-gram model that was done for data compression is something like 0.2 bits per characters. So if you think that language models is a way to understand things about the world, to reach AI, you have to agree that by optimizing this 0.2 bits per character, that's not much. You're going to learn everything about love, everything about war, everything about the world. And they're in 0.2 bits per character because this is what separates the performance of variable length n-gram model and intelligence. And that's not going to happen. So something like 10 years ago, I wrote this 0.2 bits because of simple generalization consideration. You don't have enough dynamical range. You will need humongous quantities of data to actually make progress. 10 years forward, well, they actually did it. They had humongous quantities of data, and they made a little bit of progress. So now we're probably at 0.1 bit, 0.05 bits. So do you think there is 0.05 bits per character of difference between the best BERT and knowing everything about love, everything about war, everything about life, everything about the world? You know, we're pushing a criterion that has no give. And that means that we cannot go forward in this way. It's going to stop. There is no question.
By the way, Leon, I mean, that's all of deep learning is shot through with that, right? You go to zero training error, and then you continue to train. So, but that is the mystery that many people here were trying to address.
But you don't go to zero training error with a language model. So the example I use for this to demonstrate the point that Leon just made is, train a language model on all the text ever written, except one novel by Agatha Christie, a Hercule Poirot novel by Agatha Christie. And then you give the beginning of that book to the machine until the inevitable scene at the end where Hercule Poirot says, and the murderer is, right? And now ask the language model to predict who that is. Right? I mean, I don't think any language model today will actually do particularly well on this. And that's kind of a crucial part of, in terms of perplexity, that's 0.0000001 bit. And it's, but it matters. That prediction actually matters a lot semantically.
So this is consistent even with the theory. So Sanjeev has been making this point that you can do very well for prediction, and I have some work with Greg. But getting the model right is the very last few bits are somehow critical for getting the model, and for language, like basically can show in it. This work with Greg that Chris, right? You can do everything pretty well for prediction. But if you want to do like disambiguation or something like that, it has like very little effect on your loss, but that might be everything for meaning. So
it might also be the case that you see the same perplexity for the machine as the human, essentially, but they're doing well on different things. The machine might be absolutely nailing sort of statistical regularities that people are really not sensitive to in terms of style or whatever else. And the machine might be really quite bad at things that require inference and world knowledge and so on. So I don't know. You could try taking BERT and see if it knows that Cristiano Ronaldo plays for Real Madrid or something like this. I think you'd be surprised that it's not. I'm not sure it has even that kind of knowledge. But yeah.
Well, this may be a short question because it's yes or no. But are you worried that there might be some kind of deep learning theory winter, or even deep learning winter ahead of us? Or is our job safe for the time being?
It's fine.
Well, certainly Gary Marcus is trying hard to make one. Gary Marcus is trying hard to create one. I don't think he's succeeding very well. But no. I mean, certainly there's sort of a normal renormalization of expectation because there is a lot of hype that's inevitable when people are looking for investment and grants and attention and whatever. So there's been kind of a bit of that, which is fueled also by credulity on the part of either the media or the public or funding agencies, okay? But as people learn more and more about the limitations and about the possibilities, I think there is a bit of renormalization about expectations. So I think we're in a kind of better place now than we were a few years ago when there was more hype, and now people I think are more aware of the potential and the limitations. But I mean there is enormous success that there are practical. There's big business around deep learning. Like you take deep learning out of Google and Facebook today, and both companies crumble. I mean, it's entirely built around it. So, it's not just papers at NeurIPS or whatever. It's actually kind of making those companies run. Every single car produced in Europe today comes with a driving assistance system that has a convolutional net that looks around and automatically activates the brake if there's a pedestrian in front of you or if you're too close to an obstacle. And that reduces collisions by 40%. It's an enormous number, right? It's not automated driving, it's just driving assistance. The systems that are being deployed for medical imaging that are so because of the existence of that industry and the fact that the technology is going to disseminate in all corners of the economy, I think we're not going to have a winter of the type that AI has known in the past. That said, we need to take deep learning to the next level. So we need to reduce the requirement for labeled data. We need things to work better for kind of low resource situations. We want to be able to translate every language in the world into every other language in the world. And there's quite a lot of work on this at Google and Facebook and various other places, which is very promising in that direction, using, among other things, self-supervised learning and various other stuff. We need to have some conceptual progress, in my opinion, in the direction of self-supervised learning, perhaps also in the direction of sort of marrying reasoning and deep learning, which are, at the moment, the favorite model for reasoning is incompatible with deep learning because it's discrete, it's not differentiable. And if we make those progress within a reasonable amount of time, before the people funding all of our work get tired, we're not going to have a winter, but if we take too long, maybe that's going to be a bit of a dip. So if that occurs, then deep learning will become just a tool in the toolbox without being as exciting as it was in terms of research. But it'll be a tool that will keep, and that's basically the history of AI, since the 50s, right? Niels Nelson in '66 or whatever came up with the A-star algorithm to figure out how to do path planning for the shaky robot at Stanford, and now that's used everywhere for your GPS, right? I mean, it's some refined version of it. It's just a tool in the toolbox, and everybody learns. Every undergraduate computer science student learns about shortest path algorithms and graphs in second year or something. So it's going to be the same for deep learning. Another thing that's going to happen, I think, is that the whole concept of deriving knowledge from data with the help of computers, mathematics, and statistics is going to become a discipline in itself, separate from computer science. Call it data science or whatever. But it's becoming so important for society to be able to do this. Léon used to say that many years ago, that the amount of data that is being collected by our society grows exponentially at the speed that our hard drives and communication systems grow, and that the rate of this exponential is much higher than the rate at which our brain case grow in the world, that human population. So there is a point at which there's going to be more information than any human can process, and most of the knowledge in the world is going to reside in computers and going to be produced by computers. In fact, it's already the case, probably. We already past that point. So, that's there's not going to be a winter for that reason.
Okay, I'll try to be a bit shorter. Yeah, so there wasn't exactly a yes, no question. I'm going to try to answer it as close to yes, no as I can. So let's separate that. Is deep learning going to experience a winter in the same way that I mean, deep learning, as Jan said, already works. It's not. I don't think it's going to stop working. It's like asking, is there going to be a compiler winter? I mean, I don't know. Maybe there's less excitement in compiler development now than there was some years ago. But it's not like, what? There is a compiler winter? I don't know. Well, there's interpreters. Yeah, that's true. But okay, fine. or is there a, maybe go more extreme, is there a wheel winter? Okay, I think it's very difficult to get funding now for developing wheels, but you know, they're there. There's no winter for wheels. What? Okay, the second, okay, so that's, I think, is not going to go in terms of should be worried about our jobs or about our funding. I mean, that, is maybe that's maybe a trickier question going long term, because again, as we understand things better, maybe you can automate. What?
This is not even true. Our friends working in Michelin.
Yeah, exactly. In terms of theory, you ask, is there going to be a deep learning theory winter? I feel we're now in the winter. I'm waiting for the spring. So I'm...
Yeah, okay, so a little more nuanced answer. So I think there's quite a lot of evidence just farming out the current breakthrough in a responsible way to society is going to have like tremendous impact and progress. So there's a lot of health in just taking a lot of advancements and then giving them to a broader range of things. And I think the question that's exciting is when will this current, will we hit a wall? And it's pretty clear, by these questions that it doesn't look like there's a wall, and like the slope seems very good. 2 days ago, I was just saying, look, we're going to get, literally to Sanjeev, I was saying, we're going to start seeing a lot more impressive dexterous hand manipulation, because I saw, in the last couple of months, we saw more impressive things. And then yesterday, there was this Rubik's Cube thing. So I think there's clearly a lot of slope. When that bottoms out, who knows? But just farming out what we have is going to have a huge impact. And there's a lot of implications of that, too, how we do that.
I agree with almost everything that was said, but I think if you think about a couple of natural language applications, if you think about machine translation, it could be that we're kind of asymptoting in terms of the performance of neural methods, and I'm not sure the problem is solved. So, and similarly in dialogue systems, I think we still have a long way to go. But translation would be a natural one to look at, because there's been a very, very large jump. But I feel there's some danger that we're going to get stuck with current methods, and something quite radically new is going to be needed to push that to the next level.
So I'd like to point out some limits. And the discussion I had with somebody who was looking at the wallet, and he was looking at some experiment. The experiment, I think, was the StarCraft experiment of DeepMind, trying to estimate how much it cost, and say, oh, maybe this is a $15 million experiment. Okay. So is there going to be a $100 million experiment in deep learning? Maybe. Is there going to be a $1 billion experiment? A $1 billion experiment, it's the size of the Manhattan Project, something like that. You need good reason to justify this level of investment. And you might have a kind of declining returns that are going to make, in the future, impossible to continue the same exponential growth. So there are going to be some changes. But that doesn't mean there are not going to be interesting research to do. And that doesn't mean that there are not going to be resources to do that interesting research. But maybe the way the bubble is going to burst is going to be different simply because the exponential increase is not sustainable. But that's about it.
All right, so on that note, we should probably stop. Thank you very much. Let's thank the panel. So see you all tomorrow, bright and early.